We now start our discussions on module 4 of chapter 7. In the last module, we have defined a very strong form of continuous functions called absolutely continuous functions. Recall that we had commented that a continuous function generally do not carry measurable sets into measurable sets. We have seen that a Lipschitz function has this particular property. Now, first we will see that an absolutely continuous function also has this very important property, that it carries measurable sets into measurable sets. And next we are going to define the derivatives of a function and see certain observations about them. And with this we go to the first slide of this module. We start with our first result. We first show that an absolutely continuous function f from closed interval a b to R maps sets of Lebesgue measure 0 onto sets of Lebesgue measure 0. Recall that we had investigated this particular property for Lipschitz functions also. The proof runs like this. Suppose a subset of open interval a b is a measurable set with measure 0. Let epsilon greater than 0 be given. Again, using the definition of absolute continuity, we can find a delta greater than 0 such that sigma I equal to 1 to n mod f d I minus f c I less than epsilon whenever this collection closed C I d I, where 1 less or equal to I less or equal to n is a finite collection of non-overlapping intervals in closed interval a b with the property that the sum of their lengths d I minus C I is less than delta. Choose an open set G subset of open interval a b containing A such that measure of G is less than delta. Now, we know that on the real line any open set can be expressed as countable union of mutually disjoint open intervals. So, suppose that union I equal to 1 to infinity open interval a I b I is the representation of G as the union of mutually disjoint open intervals. Now, by our assumption f is absolutely continuous and so it is uniformly continuous on each of the closed intervals a I b I. We know that the image of an interval under a continuous mapping is again an interval. So, the image of each such interval under f is again an interval. And furthermore, since f is continuous on closed interval a I b I, we know that f takes its extreme values on each such interval. So, for each I belonging to capital N, we can find a closed interval C I d I subset of closed interval a I b I such that measure of f closed AI Bi, remember that the set in the bracket is an interval, its length is equal to mod f di minus f ci. Now, note that for any positive integer k, union I equal to 1 to k open ai bi, this is subset of G, and consequently sigma I equal to 1 to k bi minus ai, this is less or equal to mu G, and this is again less than delta. So, by absolute continuity of f, we get sigma I equal to 1 to k mod f di minus f ci less than epsilon. Then we have mu star of f of a, this is less or equal to mu star of f of g, this is again less or equal to sigma I equal to 1 to infinity mu of f ai bi, and this is equal to sigma I equal to 1 to infinity mod f di minus f ci, this is less or equal to epsilon, because what we have shown that sigma I equal to 1 to k mod f di minus f ci is less than epsilon for every positive integer k. So, letting k tends to infinity, we get this particular result that sigma I equal to 1 to infinity mod f di minus f ci is also less or equal to epsilon. Now, since this is true for any epsilon greater than 0, that is we have mu star of f a less or equal to epsilon for any epsilon greater than 0, we have only one conclusion, that mu star of f a should be equal to 0 as desired. Now, we can prove the main result, that if f closed interval a b to R is absolutely continuous and B subset of closed interval a b is measurable, then f b is also measurable, that is absolutely continuous function takes a measurable set into a measurable set. So, we start with a measurable set B. We know from the characterization of measurable sets that we can find a f sigma set capital F subset of B such that mu b equal to mu f. Now, observe that the set B can be written as A union F, where A is B minus F, and since mu b equal to mu f, so mu of B minus f, that is mu A equal to 0, and F is an F sigma set. So, F can be written as countable union of closed sets F n, that is F equal to union n equal to 1 to infinity F n. Now, observe that each F I is a closed bounded subset of real numbers, and so is compact. Now, by our assumption, the function f is absolutely continuous, and so is uniformly continuous, and so is continuous, and we know that the image of a compact set under continuous mapping is again compact. So, f of capital F I is a compact subset of real numbers for each I, and we know that in the real line a set is compact if and only if it is closed and bounded. So, each f of capital F I is closed and so is measurable. Consequently, f of capital F, that is equal to union n equal to 1 to infinity f of capital F n, and so it is also measurable, and this is an F sigma set. Now, see that f of B is equal to F A union f of capital F. So, the second set f of capital F is already measurable, and since capital A has Lebesgue measure 0, so by our last theorem f of capital A also has Lebesgue measure 0 and so is measurable, and this shows that f of capital B being the union of two measurable sets is also measurable, and this completes the proof of our observation. So, this is all about absolutely continuous functions. In this module, now we start with a purpose. We want to show that any monotonically increasing function is differentiable almost everywhere, but this result is not at all easy, and we have to first consider this definition. Let f be a real valued function defined on closed interval a b. We define d upper plus f x as lim sup delta tends to 0 plus f y minus f x by y minus x, where x less than y less than x plus delta. D lower plus f x is equal to lim inf delta tends to 0 plus f y minus f x by y minus x, where x less than y less than x plus delta for any x belonging to closed A B open, and d upper minus f x equal to lim sup delta tends to 0 plus f y minus f x by y minus x, where x minus delta is less than y less than x, and d lower minus f x equal to lim inf delta tends to 0 plus f y minus f x by y minus x, where x minus delta less than y less than x for any x belonging to open A B closed. These are called upper right, lower right, upper left and lower left derivatives of f at the point x respectively. Of course, observe that from the definition the derivatives can be infinite, they always exist and they can be finite or infinite. And obviously, a function f is differentiable at the point x belonging to open interval a b if all the four derivatives exist and are equal, and f is differentiable at the end points a or b if the concerned two derivatives exist and are equal. If d upper plus f x equal to d lower plus f x, then we have a known definition, that the definition of right hand derivative, and we say that the right hand derivative of f exists. And if d upper minus f x equal to d lower minus f x, then we say that the left hand derivative exists. You are already accustomed with the notion of right hand and left hand derivative. So, in that definition, instead of taking the limit, what we are doing is that we are taking the lim sup and lim inf. So, we first give this result which states that if f from closed interval a b to r is a non-decreasing function, then all the 4 derivatives of f exist finitely almost everywhere on closed interval a b. First observe that since the function is non-decreasing, so all 4 derivatives are obviously non-negative, since f y minus f x by y minus x is always greater or equal to 0 when x is less than y. And since the proof for all the 4 derivatives are almost same, so we will only prove the assertion for d upper plus f x. So, let us write capital A as the set of all those points x belonging to closed interval a b, where d upper plus f x equal to infinity. So, if we can show that measure of a is equal to 0, then it will follow that d plus f x is finite almost everywhere. If possible, on the contrary, suppose that mu star of a is equal to beta, a positive number greater than 0. Now, since f b minus f a is finite, as f is a non-decreasing function, so choose capital K belonging to n such that f b minus f a is less than capital K into beta by 2. We can always choose such a positive integer by Archimedean property. Now, for each x belonging to capital A, from the definition of d upper plus f x, we can choose a sequence of points y x n, n belonging to capital N in closed interval a b, which converges to x, and f of y x n minus f x by y x n minus x is greater or equal to capital K for all n. This follows from the fact that the lim sup is a limit point, and so is the limit of a sequence of numbers. So, observe that the collection of closed intervals x y x n, where x runs over capital A and n runs over all positive integers. This particular collection of closed intervals, again they covers the set capital A in the sense of Vitali, because we can take these intervals as small as we like, and for each x belonging to capital A, we have infinitely many intervals containing the point x, whose lengths are decreasing as n tends to infinity. So, again using the Vitali covering theorem, we can find a finite collection of closed intervals from the above mentioned collection, say x r y r, where 1 less or equal to r less or equal to capital M, such that sigma r equal to 1 to capital M y r minus x r, this is greater than mu star A minus beta by 2, and this is equal to beta by 2. But subsequently, from the above mentioned relations, we have sigma r equal to 1 to capital M f y r minus f x r, this is greater or equal to sigma r equal to 1 to capital M capital K into y r minus x r, and this is greater or equal to capital K into beta by 2, and this is greater than f b minus f a. But see that the sum of the numbers f y r minus f x r sigma r equal to 1 to capital M, this cannot be greater than f b minus f a, because we already have f as a non-decreasing function on closed interval a b, and so it is a function of bounded variation on closed interval a b, and we know that the total variation of f on closed interval a b is actually the number f b minus f a. So, we arrive at a contradiction. So, we have shown that if we assume that mu star A is positive, then we arrive at a contradiction. So, this shows that mu star A should be equal to 0, and in other words d plus f x must be finite almost everywhere in closed interval a b, and this completes the proof of the theorem. So, to summarize, what we did in this module is that we have shown that absolutely continuous functions are very special in the sense that they carry measurable sets into measurable sets, and then we have defined the derivatives of a function, the left and right lower and upper derivatives, and we have shown that if f is non-decreasing on closed interval a b, then all the 4 derivatives exist finitely almost everywhere in closed interval a b. And with this we finish this module.